Compton is distinctive because he was actually able to perform the experiment that validated his theoretical formula about how photons should scatter off of free electrons and act like billiard balls themselves. We're going to look now at Compton's experiment and understand some of the details of how he was able to verify this wavelength shift predicted in his formula. This is a schematic representation of the experiment done by Compton. An X-ray is produced in the small tube marked T at the far left of this picture. So actually the X-ray tube is sending X-rays in all different directions, but in particular it's sending X-rays off toward a small block at R. And in this picture the X-rays are scattering off at 90 degrees toward the right, but in general he could have arranged the X-ray apparatus so that the scattered X-rays at a particular angle theta were then made to pass through a set of slits that would define that angle theta. After passing through the slits, Compton measured the wavelength, lambda prime, of the scattered photon. He did that using Bragg's law and reflection off of a crystal, shown right here. So remember that Bragg's law will tell you the wavelength of an X-ray passing by here, as long as you see the angle off of the crystal for which there's a constructive interference. He then detected this photon in his ionization chamber down at the far right hand corner of this picture. Notice that the X-rays are actually treated as particles at crucial junctures. At the scattering of the photon off of this target R, it's acting like a particle. And in the ion chamber itself, it's going to be registered as if it's a particle. But interestingly enough, Compton was using the wave properties of this X-ray when he was reflecting it off of a crystal so as to measure the wavelength. Here's what Compton found. This is a graph of intensity of X-rays as a function of, on the horizontal axis, the wavelength of these X-rays as measured in that ionization chamber and the Bragg's law formula for constructive interference off that crystal. So he's measuring wavelength here on the horizontal axis for several angles theta for scattering off of the target R. So these thetas are the angle of scatter, not the angle of the Bragg reflection. At each angle theta, he measured the wavelength of lambda prime of these X-rays again by tilting that crystal and finding where is their constructive interference. Notice that there's always a peak at lambda prime equal to the original wavelength. So here's 0 degrees. Remember, there's no wavelength shift predicted for 0 degrees. And that peak is present in all the plots down below. In other words, there's always a peak in the scattered wavelengths equal to the original wavelength. That's just because scattering can also take place off of protons. And in the Compton formula, if the mass of the electron is substituted out for the mass of the proton, the wavelength shift is very small. But for all angles greater than 0 degrees, there's a second peak with lambda prime greater than lambda, and that's coming from scattering off of the electrons. The wavelength shift that was found in these graphs agreed very well with the formula originally attained by Compton. In this way, he was able to confirm that photons do have particle-like behavior because they scatter like billiard balls, and the momentum shift that they have as a result of elastic scattering is exactly that which you expect from billiard ball type scattering in first-year physics.